Okay, cool. Well, today I'm excited to have Laura Norman from the United States Geological Survey. Welcome.
Thank you.
Cool. So yeah, do you want to just say a little bit about what you do, and then maybe we could then go back in time a little bit about how you got started. But yeah, so what is it that you do with the USGS?
I am a supervisory research physical scientist. I've been working at the U.S. Geological Survey since 1998, and I study watershed modeling and all of the components of the water budget related to dryland regions. And so my research has been looking at how people can impact water budget parameters in models and trying to develop scenarios that are beneficial for management.
Okay, cool. So water budget meaning like more water or less water for the people, kind of.
Water budget meaning like the water cycle. So I look at all the components of the water cycle. So everything that comes into a watershed, what
Mm.
happens to the water when it is here, and how it leaves.
Okay, cool. Cool. Well, let's jump back a little bit in time before that. So, how did you get interested in water and land?
Well, I am originally from the swamps of Rhode Island. And so I grew up in a wetland in the coastal region of New England
Mm.
and went to school at Oregon State, where I studied forestry. And I was very interested in the big trees in the Pacific Northwest and maintenance of big trees. And I ended up learning about watersheds when I was there. So I took a job with the state parks and some other jobs in between. It ended up coming back to school to the University of Arizona, which is a water limited area here in the desert, the Sonoran Desert. And started studying watersheds here and the arid lands and trying to figure out how to best manage water. So.
Cool. And then, how did you work for a while before you ended up with the USGS, or you immediately went there?
Well, I did, had a couple seasonal things, internships and such. But when I came to Tucson, I got a job working for the university doing geospatial analysis. So my expertise in my master's degree in watershed management was the advanced resource technology option. So I was using GIS, and then when I did my dissertation, started employing remotely sensed data. So using satellite imagery within a GIS, within models. And so I worked for the University of Arizona for a couple of years and then started volunteering at the USGS until I was finally contracted on.
Okay, cool. And do you want to explain to the audience what GIS is?
GIS is Geographic Information Systems, and so it's basically making maps. So I use a lot of different data. I mentioned satellite imagery, but a lot of people these days are most familiar with GPS, so global positioning systems. So using that type of geospatial data within a computer software to develop maps and do analysis in a spatial context.
Cool. And then the USGS, which is the United States Geological Survey, which is kind of a intriguing name because I don't think most people know what a geological survey is. What does it do exactly, and how big is it?
Okay, so I think the USGS has like 6,000 employees all over the country, and we currently have 6 mission areas. I work in the core science systems mission area, but we have um, biological resources, water resources, geologic resources, and so it's divided out into these types of things. Most people that are familiar with the USGS are familiar with us because of our topographic maps. So when you go to, go for a hike in the forest, you get out your map, and that's the USGS map. And we've, been kind of made popular with the lay people for that reason. But we also have our hazards and minerals explorations. And so when you hear about an earthquake or a flood event or volcano, that's the USGS will be the first person to be contacted in response for that. So we have a lot of different science. We're the science arm for the Department of Interior. So we do all the science for the parks, the BLM, Fish and Wildlife Service, and BIA, Bureau of Reclamation. So that's our hat.
Okay, cool. And BLM is Bureau of Land Management, so all the national land, I guess.
Yep. A lot of the national land, but not the Department of Ag. So Forest Service falls in that part, but we're the Department of Interior. So.
Okay, cool. And geological survey, I take it means surveying all the geographical features like the land, the rivers, how the water's working. Like
Yeah, that's what it has become. I think originally we were a little more focused on the geology, but of course we still are focused on geology. We just kind of broadened our scope to include some more of the geographic features.
Okay, cool. And so the people who are doing the water resource management in the US, I guess they need to know some of the science of how the water's moving through the landscape. And so that's where the USGS comes in play, right? They try to understand the hydrological cycle and how it interacts with the ecosystem.
Yep, 100%. We have gauges all over the US monitoring surface water flows. We monitor wells, and we have protocol to make that information available online in real time. And so it's, we're a public service agent. And so civil servants, everything that we do is made available to the public.
Okay, cool. And so what was it, your project when you came to the USGS to do?
I started working on a geologic map of the US-Mexico border. So I was digitizing, putting old geologic maps into geographic information systems. Started analyzing those in relationship to environmental health in the US-Mexico border. And that evolved into mapping colonias that did not have adequate infrastructure, such as sewer lines or water lines or adequate housing, and trying to identify those communities, or what they're called colonias on the US-Mexico border, that needed to have some recognition for that lack of infrastructure. So I started working on projects like that. Funding came from the Department of Housing and Urban Development, and working with partners on both sides of the border to do that, both of those, or all three of those projects. And then I started doing some watershed modeling, looking at how flooding might impact the infrastructure and also the housing communities that I had been mapping.
Which towns were getting flooded or were in danger of being flooded?
Well, one of the biggest flood hazards for the state of Arizona is the city of Nogales, Arizona, which has a sister city on the Sonoran side, Nogales, Sonora, so ambos, Nogales. And that was where I ended up doing most of my dissertation research, looking at the impacts of flooding in the floodplains there. But there's flood issues in a lot of desert towns. It's kind of surprising to people because you think there's not a lot of water, but when it does rain, the systems are really not equipped to handle high energy and high amounts of or volume of water. So it becomes hazardous.
So yeah, I guess there are different types of solutions for floods, right? There's nature-based solutions, and then there's also the dam levee solution. So do you want to say a little bit about that kind of that?
Yeah, I have only studied the nature-based solutions, and one of the first structures that I started looking at was looking at gabions, which are rock structures that can be installed in channels. They're wrapped in chicken wire, and they're very popular in Mexico and in Europe and in other dryland regions and different countries, but not very popular in the United States for looking at flood detention. So we looked at the impacts of putting some rock gabions around the city of Ambos, Nogales, and modeled the impacts of different locations and size of structures, trying to prioritize areas that would benefit from that type of solution.
And where do you put these gabions?
A lot of people use gabions to line the banks of sandy arroyos. So our streams are very very mobile. The sediment moves very quickly in our dryland streams, and so they can be used to line the banks. But in this case, they were being used to across the width of the stream channels. So in series, putting in structures. In Nogales, they ended up putting in engineering quite a few. I think 15 structures have been put in, and the flood detention is great.
Cool. So they're kind of like a check dam or a beaver dam analog in some ways, right?
Yeah, and I actually have been trying to make that connection because there's a lot of people that are interested in beaver dams and beaver dam analogs these days in wetter parts of the country, but in the desert Southwest, beavers have a harder time existing because we don't have so many perennial water supplies. And so in our region, which is the Madrean Archipelago ecoregion, people have been installing rock detention structures for thousands of years. So we've dated structures. There have been studies in almost every culture in this ecoregion for which dryland farmers were using rock detention structures to help with farming. So that's a lot of those are still in the landscape today. So it's pretty natural. It comes natural when you start thinking about it, especially in relationship to the wonderful ecosystem services that the beavers provide for people. People can be the beaver.
Mm. And how does it help the farmlands?
So you slow the flows, you reduce the flood detention, reduce the flooding. So in like I mentioned, these dryland arroyos, when a big event comes through, sometimes that can just wash a crop out downstream. But most people try to take advantage of the rainfall as irrigation here, and in the past, of course, that's what they were doing. In addition to slowing the flows, you are accumulating sediment. We've had studies that have documented increased organic matter behind structures, increased vegetation response behind structures, and so that's something that those dryland farmers were taking advantage of for their crops.
Oh, so this whole, because in the permaculture world, there's this whole slow water. Brock Dolman, slow it, sink it, spread it, and Erica Geist promoting that slow water. So, and I guess I think some people would be interested to know that the USGS, like this formal body, is interested in all this about slowing the water.
Yeah. I got to meet Brock last year and got to visit his farm in California. I was truly amazed by his energy. I've met Erica as well. Truly impressive person that I admire her books and writing. So it's just kind of, I think, kind of a movement that started, and we all kind of got on board around the same time without knowing about each other, but using different avenues to explore and express and find different results. So yeah.
Do you know how the USGS got interested in the slow water ideas?
Well, my project is unique in the USGS, and so I had been looking at ways to develop scenarios that would benefit the people that were living in the Twin Cities of Nogales, and I started modeling different scenarios and got the International Boundary and Water Commission, which is part of the Department of State, to fund my research to look at the potential of putting those structures in to reduce flooding there in 2010. And then I was at a conference and I saw this fantastic scientist, Ron Pulliam, talking about some structures that he was studying that looked exactly like the gabions we were putting in at Nogales at another location on the border, where they were using the gabions to create habitat. And so I kind of went like that, kind of like fell into this new vein of research. And we looked at those structures. And when we looked at those structures, we were looking at the increased vegetation. And we found that where there were structures, there was more water availability, evidenced by increased vegetation, or at least maintained vegetation over a 27-year drought period, up to 5 kilometers downstream from each structure and 1 kilometer upstream from each structure. And that was really kind of a turning point for me, because a lot of people were concerned about structures stealing water from downstream users. And my research identified in that one scenario, and then many more scenarios, that the structures actually protect the water from being evaporated in our hot and dry desert ecosystem by putting it underground and making more water available downstream to the users. So that was kind of the kickoff to the rest of the research that I've been doing.
Oh, cool. Yeah. So you found out from the gabions that it actually caused to go into aquifers and then kind of come up again further downstream. Is that okay? Cool. And then you who proposed to the USGS to do this kind of gabion slow water idea, kind of.
Well, I proposed to a couple different people. The USGS has been supportive of my research since I began working here, but I've also had a lot of outside support from different departments of the Interior, and also private funding to do studies to look at these potentials. So the work at Nogales, I mentioned International Boundary and Water Commission, and looking at the San Bernardino National Wildlife Refuge. We had some support from the Bureau of Land Management just north of there, and the Fish and Wildlife Service was cooperating with us at that time. And so it's been kind of almost a grassroots style effort in developing projects and getting funding to do science, but with the USGS backing. And when we do projects at the USGS, we have these standardized protocols, and we're mandated to do unbiased science. And so we have this rigor that's associated with our science that is very nice for adapting across different landscapes.
Cool. Yeah, it's nice to hear that that this research is going on in the kind of more the U.S. departments. I mean, however you call USGS, I guess it's called a U.S. department, right? So and so when you did the gabions, you found how far away did the water get impacted? Like, say so you're shifting the hydrology. Does it shift the hydrology at the watershed level, or how far would you say the impact goes for putting a local gabion?
That's a good question. I haven't really found the boundaries of the impacts yet, but I've had a couple different studies looking at the hydrology, not just the flood detention, but the water provision. So I mentioned the vegetation study that we did in San Bernardino, but we've also looked at water volumes. So in the El Coronado Ranch in the Chiricahua National Forest, we looked at a stream that had been treated with over 2,000 little rock check dams, and we looked at a watershed right next door and compared the runoff in both watersheds, because they're adjacent and had similar climate and similar elevation and similar vegetation. And one was much larger than the other, but when we calibrated it for size, we found that the watershed that was treated with structures had reduced those reduced peak flows that we saw in Nogales associated with the larger gabions, but then they also had more water coming out of the system, so 28% more volume coming out of the system, which is a really big deal in dryland watersheds, as you can imagine. But what was really interesting too to think about is that the watersheds were delayed flows. So in addition to having more water, the water was coming out 3 to 4 weeks longer than in the watershed that didn't have the structures. And so, that too associated when you asked what were the dryland farmers looking for with the structures, I think that in enhancing their growing season was one of the benefits that they found.
So, oh, yeah, cool. So when you say 28%, so you're saying, okay, so the water gets delayed, so the peak goes down, but then it's coming out 3 to 4 weeks later, and then that 3 to 4 weeks, that's the 28% that's
It wasn't just the timing, though, it was the amount of water. So when you think about if you have a bare surface and in the watershed that didn't have structures, it was just, bedrock channel, and you take a glass of water and you throw it down the channel, and it would just kind of like wash down the channel, and it would be exposed to the atmosphere because there's nothing holding it. And so in our area, it's very low humidity, low relative humidity. And so everything just kind of gets sucked right out into the air. So like, for example, when I lived in San Francisco, I'd get out of the shower and my towel would be wet for 2 days. In Arizona, when you get out of the shower, your towel's dry in an hour or two. Like the atmosphere is just sucking the water out of the system. So when it's exposed in that bedrock channel, the water kind of gets lost to evaporation. But in the channel that had the structures, it was holding the water back and hiding it and tucking it into the dirt that was being collected behind those 2,000 structures and creating what we had hypothesized at the time were perched aquifers at each of those 2,000 little structures. So those are like little wetlands where the water was being held underground and then slowly released. And so the water that's running in the stream was more at that location because it wasn't getting sucked out by the atmosphere.
What's a perched aquifer?
So a perched aquifer it's a small, well, in this case, we were imagining a small kind of sponge that was existing on top of the rocks that formed the channel. So later studies that I've done, most recently I published a paper about leaky weirs and managed aquifer recharge that occurs at large structures and I think at all of the structures, and really just realizing that those perched aquifers that we hypothesized at El Coronado Ranch were potentially just that alluvial storage that was created by the structure. So by really holding, that sediment back, I've kind of gone from, oh, it's the vegetation, it's the rocks, now I'm kind of like, it's the dirt, but it's that combination of that soil, water, carbon sink that occurs when a structure gets put into place where sediment is captured and becomes, just this rich, ripe, growing, fertile ground for storing water and growing plants, and that just wouldn't be there otherwise. So people are like, well, what's the difference? If you have the structure there and you didn't, well, you wouldn't have those nice little sponges behind each structure, and that each addition of sponge is additional storage. So you wouldn't have that storage.
And how deep does that go underneath the creek bed?
It depends. All of our findings are really place-based and dependent on the geology and everything. So in the case where something's built on a bedrock surface, then it might not go, that deep. But when you have your structures there, and you've got sediment being deposited, the water gets captured at the structures. And what we found is that the water then starts getting pushed out around the structures. So what's called lateral flow. So it pushes the water out into the banks and underneath the structures when there's faults or the opportunity for water to go there. So if it pushes it back upstream, might get behind the bedrock, depending. But all the superficial aquifers get inundated, and then we'll start releasing water downstream. But in some cases, you might have fractures or faults or springs that are conduits to the deeper groundwater. And in that case, it could go very deep.
Mm. Cool. So yeah, so the farmers like this because now you have like one more month of like water into the dry season, I take it, right? And
Yes. And the other thing that we most recently found, and that we are working on right now, is that the areas that have been treated by structures become wetlands. So wetlands in areas where there were historic wetlands that got restored, but also wetlands in areas that weren't, where wetlands were created by structures. And at all of the wetlands, we see a greening up earlier in the season. So that extension might not just be on the fall side of our monsoon season, but also in the spring, a month or two earlier, greening up. So really extending the growing season, which is a pretty big deal.
and how far do these wetlands extend past the river banks? Like, how much wider are they?
I don't have an answer for you there. I will tell you that we are documenting that lateral flow into the banks and out, but we have we did a vegetation study and looked at vegetation in the channels and on a yearly basis, and we're completing that on every 5 years in the overbanks to see what the impacts are in the field, out into the edges. And so hopefully we'll have some results to share with you on that as well. But it is, as water accumulates, it gets pushed out. It gets pushed out and it gets pushed down and it gets pushed under the structure. So it creates, this series of chain of pools or chain of wetlands when you have a lot of them.
And is that the natural state of rivers in the past, like wetland, like because I was talking to Stuart Andrews from Australia, and he was saying that's the natural state in Australia, like before we messed up the whole water cycle. Like we'd have these series of ponds, like it's kind of like a bead structure, kind of.
Yeah, what do they call it? A chain of pearls or something?
Yeah.
Yeah, I've heard that before from the Malone Institute. That aspiration. In our neck of the woods, I'm not exactly sure. I do know that in a lot of the locations that we do research in, and where people are putting structures in, is in response to erosion and gullying. And so in areas that formerly were not degraded, they're getting degraded, and head cuts, and the gullying is just traveling up the stream with no end, and basically draining all of those grasslands or shrublands or whatever is around it. So it's creating these avenues or these gravity fed drainages of previously wetter areas, and so when you plug those up, you can kind of create what used to be there. And we see in most of those locations, when you're walking in the arroyo, you can see the banks and you see the large cobble of historic kind of riverbeds and paleo channels kind of at the surface. And so it's just a wetter environment that that was able to be maintained. And so kind of, people came in and we brought our cows and our cut our roads. And, these are all things that cause erosion and, pumping the groundwater and all the things that we do. So it is just kind of a maintenance to go back and plug those back up afterwards. And that's actually what I had learned when I was at Oregon State in the forestry department, because the foresters were trying to manage their erosion from the roads that they were cutting.
And what's the paleo channel?
Historic riverbeds. So you can see in the soils, and you can see underground, where the rivers used to flow. So in some cases, in more steep slopes, you might see nice meanders, and kind of you want to, or like a natural system, a river will kind of just move back and forth, depending on flows, and push it sediment around, and vegetation will respond. But when you unplug that channel, then it creates this hard kind of line in the landscapes, where the water just gets funneled through and you lose it all. And so in the paleo channels and the historic channels, even looking, in the 1935 aerial photos from the Colorado River, you can see a lot of meander that has been managed today with urban development, and channelizing our streams. So trying to put that wiggle back is another solution to slowing the flows.
Mm. And then for the farmlands, that the farmers are happy about this, is it because they can get the water out of the river, or that the water is actually seeping underneath their land and actually giving them more, at a deeper level underneath their land, that there's also water?
I think both, because the water is available at the surface, so that's where you'll see the cattle will go to the stock ponds where there's river flow. Then we'd see a lot of wildlife there. We've had scientists that have put cameras around areas that have structures and areas that don't have structures, and that it's very interesting to see the wildlife are really in tune. They've just got the sense to know to come and get a drink where there's standing waters, and bears go and play in the pools, and then like I said, the standing water is there. So there is water available at the surface. You see, dragonfly larvae and these things that wouldn't be in these areas otherwise. But the vegetation as well. I think the ancient farmers probably took advantage of both.
Mm. So these ponds are also, are you saying they're forming actually laterally away from the river? Like there'll be new ponds forming?
No, kind of on the river, adjacent to the river. So kind of like you were describing the Australian
Oh, right. Okay.
pools.
But and then on the farmlands adjacent, is it seeping that far laterally, so that their land is getting extra water?
Yeah. So as it flattens out and you've got your floodplains, that's where a lot of the farming used to occur in the desert. So like the Hohokam farmers, we had a lot of canal systems that are still evident on the landscape today. So there was a lot of manipulating the surface in order to irrigate different crops depending on the style. But for sure, by connecting the rivers to the floodplains and making that surface all just saturated and soaking wet, and having that water available for longer periods of time, having more water available.
Mm. Cool. So yeah, so this is kind of cool because it looks like you're just doing something on the river itself, like putting a gabion or some rocks there. But in fact, it actually affects a much wider area laterally, like that's kind of hydrating a whole extra area.
For sure. Yeah, we've had studies looking at temperature too. And so around where there's rock structures, you see a decrease in temperature after rainfall that can be held for a couple days, bringing the temperature down just a couple degrees. But that can be a really big deal when you have thousands of structures and they're all situated, nearby each other. So you kind of are able to, create microclimate impacts where there are structures. Because of the decreased temperature, but also because of the increased vegetation, which would then further decrease the temperature.
Mm. And this is cool too, right? Because you're saying they're having flooding issues, but it's now slowing the water down so it doesn't flood downstream further. Is that right?
Yeah, so reducing the flood hazards, reducing the drought hazards, reducing food security hazards,
Mm.
helps to keep sediment in the ground, so increasing our air quality, increasing our water quality. Yeah, there's a lot of ecosystem services that we've been able to unveil related to rock detention structures.
And do you think it also reduces wildfire risk because it's more hydrated in the floodplains now?
Yeah, taking a cue from our colleague Emily Fairfax and her work, Joe Wheaton looking at the reduction of wildfire around beaver dams and their analogs in Idaho and and now I guess she's in Michigan, I think. But yeah, I think that the impacts of rock detention structures are the same. In our study area at the El Coronado Ranch, there was a huge fire that came through the mountains where our watershed, our treated watershed was, and the fire did go very lightly around the perimeter of that watershed and burnt most of the mountain pretty severely. Now, I don't have evidence that supports that aside from that qualitative assessment, but it is something that I would think makes sense to me because it's much harder to burn something that's soaking wet than not. And in fact, it's the same if you have a beetle infestation or other trauma associated with forests that, if you have a healthy and wet, thriving forest versus a stressed, dry forest, then they're more, resilient.
Mm. So in California, they're having a huge amounts of trees dying off because of beetle infestation. So you think these check dams or these gabions might be a solution?
Maybe. I haven't done that study either, but they definitely do make the vegetation much more healthy and drought resistant.
Mm. So so if you so when you say you had 2,000 of these like in an area, like how big of an area was this?
That was a 769 square kilometer watershed. So basically, you could, as you walk up the stream or the arroyo that now is a perennial pools,
Mm-hmm.
you can see a structure, at least three structures all the time as you're walking up, depending on how the slope is.
Mm. So you're affecting the watershed hydrology at this 700 square kilometer scale, like by putting these 2,000 gabions in.
Yeah, and I did a little like back of the envelope study to see, how many structures, like for the state of Arizona, you would need to put in at that density that they had done at the El Coronado Ranch, and found something like 80,000 structures, I think, and that would be, I forget, maybe $100 million. And I thought, that's crazy. That's so much money, and that's so many structures. But if you put that density in on all of the federal and tribal lands in the state of Arizona, that's how many structures you would need to put in. And but then I thought, well, and I published that too, that the state of Arizona spent $100 million in flood post-fire flood recovery in 1 year alone. And so, doing some kind of preemptive work to try to, get a handle on the fires and the floods might be worth the investment, because there's so many other benefits that come along with those, fire and flood potentials. So, in the case of fire, what I'm talking about is that post-fire erosion that occurs, and then with the erosion and water runoff in a rainstorm, then flooding. So, and then in the state of Arizona, you think, well, that's, how many, 180,000 structures. But in the state of Arizona, the CCC in the 40s put in over 500,000 erosion control structures. And so there was a time that we were out on the landscape doing this kind of work regularly. And so it's possible. It's been done in the past, by 6 times as many structures.
Wow. So the CCC is the civilian corps, right? Like
Civilian Conservation Corps. Mm-hmm.
yeah, that was around a long time ago in the U.S. And So they did stuff like this. Amazing.
Yep.
So yeah, I mean, it does seem to me like using these rocks is a much more, I mean, it's a nature-based solution. It's a much more mild way of, I mean, it seems like it's helping restore the water cycle as opposed to a normal way of building bigger and bigger reservoirs and then aqueducting the water in. And, like the Colorado River right now is being under threat because we're taking so much water. So if in Arizona there are more of these gabion structures, you don't need to take as much water from the Colorado River or pipe it in. So,
Maybe not.
yeah, because it seems like the farmers could get a month more extra hydration. So yeah, it's kind of amazing. Like this kind of solution can help with drought, with floods, with wildfire, and with getting water to farmers. And yeah,
Yeah, yeah, and what's really amazing, I mean, I'm a high tech girl. I work in a high tech world on my computer all the time, but this is a really low tech solution, and it's low cost and low investment with a lot of benefits for sure.
so it's so amazing. How come you think it's not more known?
I think there's been a lot of misunderstandings about structures, and the biggest is that people think that the structures are stealing water from the downstream user, and that just isn't the case. So, as I am hoping that as science is able to continue to develop these studies and create these metrics describing the impacts of structures, that more people will be enthused to start using them, and that some of the restrictions on permitting can be lifted.
Right. Well, I have this metaphor I use to try and explain it. So, like, if you have a museum and you have people coming in, and so you maybe have this rush of people coming in, like that's like a big storm. And then if there's not that interesting a museum, people will just kind of come out again very quickly, right? But if you have a lot of really interesting exhibits or something, then people may stay for 2 hours, 3 hours. And so, and maybe in the past, like no one was coming out in the afternoon because they'd all gone in the morning, come out by the morning. But now you've actually delayed their staying, and so they're trickling out all through the afternoon. And so you're still getting the same flows out because the people have to leave the museum. So you're not losing the water just by all you're doing is slowing it down so that the people are staying in the museum longer and then coming out again. And so yeah, so the total water is still, you're not losing the water by building these check dams.
Yeah, and I would say, in this case, people aren't being evaporated into the sky at the museum, but we do see that tucking the water into the landscapes behind the structures really helps to keep it around and makes it so that more people come out of the museum than they would if unless they were being evaporated out.
Cool. And you've come up, you had a name that I hadn't heard before, NIDS, right, for these kind of structures. What does that stand for?
Natural infrastructure and dryland streams.
Okay. And where did that name come from?
Well, I started working with the scientists around the country, some of the beaver scientists and soil carbon scientists, and Michael Pollock and others talking about these different types of structures, and everybody's kind of got their own name for them. Is it one rock dams or Zuni bowls or earthworks or weirs or check dams, and so we wanted to just try to lump the beaver dams and the beaver dam analogs, whether they were wicker weirs or there's a lot of different names. So we just said, let's call them NIDS and include them in the whole category. And because
Right.
what we were finding is that the impacts of whatever type of structure, as long as they leak, as long as it's a permeable structure, it's not damming the stream, but just slowing the flows.
Right. Yeah. Because I guess it does have many origins. Like many cultures have discovered them. Like I know in the Middle East, the Fertile Crescent, they had these gabions, and then in Peru they had these slowing. So like yeah, and they've all kind of, I guess each of these cultures then has its own name. And then there was different groups like permaculture, which study a lot of these structures, and then renamed them earthworks. And
Yeah.
so yeah, so now we have tons of names. So yeah, and it is interesting that it's been rediscovered so many times, and maybe I guess yeah, like hopefully, I mean it does seem like hydrology, the Western science of hydrology, it was in the 50s, really focused on big dams and big aqueducts. But it seems like in the 80s and 90s, they became more interested in, or it started becoming more interested in nature-based solutions. So there's this shift in hydrology to now, oh, these things that we discovered in ancient times now actually might be really good for us to do still.
Yeah, go figure, huh? Yeah, it is. It is nice though, to be able to get some of it documented, and hopefully, then we can make the next step, to changing some of those policies and mindsets so that more structures can be installed.
And so there is a whole world of hydrological modeling and groundwater modeling, and that all these hydrologists do. How many of them now are starting to look at NIDS, or like these kind of slow how slow water systems affect the whole hydrology and doing that modeling?
Well, I don't know of too many in the United States, but there certainly are a lot, in China, people that have been studying the impacts of structures in the Laos Plateau for a long time. I'm often citing that in the Middle East, to sand dams in Africa. So it's just something that is kind of coming back to the United States at this time, but wasn't really forgotten in Mexico or some of these other dryland regions. So, um, yeah, I think more and more are now.
And so they're doing this hydrological modeling in China in the Laos Plateau where they're
Yes.
doing it slowing. Okay, cool. And do you know anything about what they found with this hydrological modeling? Or?
Similar effects. So we often cite each other. When I get requests to review a paper for a journal, it's often on looking at the impacts of different structures in different locations, and vice versa. And so, become more and more aware of different people's research in different countries.
Okay, cool. And in China, was it stream flows slowing, or was it they were doing other types of slow water stuff?
Yep, watershed modeling. So looking at like trinchera style structures. So looking at hill slopes and putting in structures on the hill slopes to slow flows. A lot of check dams in the riparian areas.
Okay.
Mhm.
And then also because China had, millions of people had evacuated because of certain huge floods. So they had this whole sponge city movement now. Like I think many cities are trying to absorb more of the rainfall, and I assume they probably do hydrological modeling when they study and create all these sponge cities in China.
Yeah, modeling is really useful for doing planning. Trying to predict where to get the biggest bang for the buck. Is this structure gonna create the recharge, or whatever it is you're putting structures in for? Is it to slow flows, or arrest gullying, or increase recharge? So you can use models to try to predict, which areas might be most receptive to putting structures in. So I often use models that way, but also I use models. So if we get measurements out in a watershed, then I can use a model to extrapolate. So taking the measurement at one site and then kind of folding it out into the rest of the watershed to see what those impacts would be if you put more structures there, or if there were structures there, you could see what that would be at a larger scale.
And what about the modeling of the hydrogeology, the aquifers? Because I know it's kind of hard to model the aquifers because it's so complex how it's seeping, and everywhere the rock formations are different. Like, are people doing that too, to model how much the aquifers are refilling when you put in slow water structures?
Yes, and we're doing a project right now in La Paz, Baja California Sur, looking at the impacts on the groundwater aquifers and using groundwater models. We also use groundwater models to interface with watershed models to look at the surface to groundwater interactions at a project here in the San Pedro River, the Baba Kamari Ranch. But what we find, in some of those deeper aquifers is you have water that's older, and so it's a little harder to track whether or not there's a change in recharge around a structure when the groundwater is not getting recharged for 60 to 1,000 years. So talking about like that is, it's hard to really get get that documented. But we are using our understanding of the geology to look at fractures and conduits to the deeper groundwater. So making assumptions there. We have a study where we're putting dye behind structures and then looking at the time for that dye to reach a potable supply well downstream. And so we have some studies looking at that. But again, when you're talking about groundwater, sometimes the age is difficult to monitor.
Cool. That's cool that you're doing that modeling. And then there's also this effect where trees can bring up the water, right? Hydraulic redistribution, where the tree roots can bring up that aquifer water. And so I guess, are there people modeling that too? Like, so as you slow the water down to recharge aquifers, actually there's more water available to the whole ecosystem because plants can bring it up now.
Yeah. That ET cycle is another thing, that evapotranspiration. So looking at how plants are using the water and how plants impact the water budget is definitely a focus of our research all over dryland areas, because just looking at the impacts on the climate. I mentioned the shade potential, the fact that when water is in the environment, it's a little bit cooler. And so it's a very interesting cycle that seems, as you degrade a system, I always think of like that snowball effect. You get a gully and it just starts unraveling. The whole system becomes unraveled and it just drains out. But it's the same for restoration. When you put a structure in, the whole system kind of snowballs back the other way. And so like all the processes kind of work together to roll it back up, to sew it back in. And so it really is, it's really phenomenal.
Cool. Yeah, and this whole water budget idea, right? There's like, because I think maybe a lot of listeners may not have heard of this idea, water budget, but basically it's a fundamental concept in hydrology where you have the inputs and you have the outputs of the water budget, right? So you have the precipitation, and then you have the stream flow, which can be an input, but then it can also be an output, and through the aquifers and where it goes down and goes up. And so like you put all these things into an equation.
Yeah. People often think of, a bathtub, and you've got, the bathtub is there, and then you have the water coming in, the precipitation, and then you have this much water in your bathtub, and that's your storage. And as the water, leaves the bathtub, that's the change in storage. And so then you have the drain, you have the surface water coming out, you have water going into the earth, so into groundwater, you have other water coming up from the ground, and then you have the water leaving with either evaporation or transpiration with plants. So that's the full cycle in a nutshell.
Right. Yeah.
In a bathtub.
Yeah, I think it's kind of cool because sometimes you can kind of forget where the water could come from, or like there's like, and I think people sometimes forget that if you recharge the aquifers, you can give more water to the plants through that, that part of the water budget, or through the tree roots bringing it up, and it's kind of a forgotten part.
Yeah, I remember when somebody first mentioned to me the idea to rehabilitate a spring. I thought, well, how can you make more water come out of a spring? That doesn't really make sense. And then I saw, that occurring at the Cienega Ranch, where leaky weirs were put in, and an old spring that had kind of dried up had this new bank put in, a new water bank, and the water budget there was increased because of the storage. And so it allowed the spring then to recharge and start expressing water into the arroyo again. And so it is really fantastic to think about that.
Cool. And is the term slow water in the hydrology world? Is that a term?
It is now.
Okay.
But yeah.
Okay. And are people, is it just very few people studying how slow water affects the whole hydrology system, or there's beginning to be a bit of a movement studying it?
Yeah, I think that more people are interested. We've definitely had people come to us and ask us to look at different projects, and is this actually changing things? And most hydrologists understand that if you're slowing the flows, there's more opportunity for infiltration. And so it seems kind of common sense for people that have studied water their whole lives. But then when you put the application in the real world application, it kind of marries, the professional to the private. You think, oh, this is something we can do ourselves at the surface.
Yeah, I remember like we were in Spain and we were talking to some of the city hydrologists or the municipal hydrologists, and they were like they were getting too much water in the wet season and then not enough for the people. There was water shortages and even they had to turn off the taps in the dry season. And so their problem was moving the water from wet season and dry season. And I was with some of these more water cycle restoration people, and we're like, well, you can actually slow the water, with stuff like these check dams and all this. But it seemed like the city or the municipal hydrologists they weren't aware of these techniques.
Yeah, it's funny. I learned about, check dams in relationship to erosion control, in my watershed management classes and, taking it to the next level. Well, yes, of course, it's going to slow the flows. That's why it's controlling the erosion. But yeah, you kind of stepping back through, the lessons and seeing all of the different impacts.
Right. I mean, in some sense, one of the central issues ever since, thousands of years ago, hydrology is that how do you get the water from the wet season to the dry season, right? So that is kind of the central thing. It's just that I think we've kind of moved to this dam aqueduct model, or at least in the 50s, we're moving away a bit from it now. But that became the idea of how you get the water. You just collect the water from the wet season in the big man-made dams, and then you just divvy it out through the aqueducts. But we've forgotten that there's these more simple, low-tech, natural solutions kind of do it.
Yep.
Cool. Is there anything else you want to share about your work or this whole?
No, I'm happy that you're interested, though. Thank you so much.
Yeah, cool. And are there future projects that you're looking towards, or the USGS is looking in this area towards?
We've had a couple ideas talking about potential for growing specific crops behind structures. Is there a way to increase range production? Is there the potential to grow mushrooms or other specific crops behind structures? Can you accelerate with compost? We have a couple ideas that are kind of coming up, but right now just trying to get some publications out describing the cienagas and the extended seasons, and our research down in Mexico looking at water augmentation. So getting those wrapped up first.
Okay, cool. And if people are interested in finding out more about you have a staff page on the USGS page, right?
Yeah, the arid land water harvesting study. So you can Google that and find it, or you could Google my name in the USGS to get to that page.
Okay, cool. And then are there any papers that you might suggest people? I'm sure you've written a lot. Are there any particular papers that people might want to take a look at?
Yeah, that summary paper that introduces the NIDS topic would be a great starting point. We have some beautiful graphics that were developed by Heartwood Visuals describing 20 years of papers, 20 years of research of my own, but also some of my colleagues, Ellen Wohl and Michael Pollack, Emily Fairfax, Ratan Lal, and Alan Gallis, comparing our research around Western United States, looking at the different types of structures. So that's the NIDS, NIDS, Natural Infrastructure in Dryland Streams paper. And then my most recent publication. It is Natural Infrastructure in Dryland Streams something.
Okay. That's okay. The scientific titles are so convoluted sometimes. It's hard to remember.
Yeah, and then the other one would be my latest publication about leaky weirs and managed aquifer recharge.
Okay.
I can read the title off if you want.
Okay, yeah, let's hear it, yeah.
Natural infrastructure in dryland streams, NIDS, can establish regenerative wetland sinks that reverse desertification and strengthen climate resilience. And that's a 2022 paper from Science of the Total Environment.
Oh, cool. Oh, great title.
It's a long
Great
one.
title as science titles go. It explains what you're actually doing nicely, clearly.
Yeah. Thanks.
Cool. Well, cool. Well, thank you so much for coming on today. I really appreciate it.
Yeah, nice to see you, and I appreciate your interest, like I said. So keep following you.
Okay, cool. Thank you.